In this video, we'll be talking about a number of issues associated with multiple linear regression analysis. First of all, we'll start with data scaling and its effect on OLS statistics. Now, why do we need a data scaling? Sometimes maybe we would like to change the units of measure of the data, maybe to improve the interpretation. We might want to get rid of decimal places in our coefficient estimates. Yeah, in that case, we need to rescale the data. Yeah, maybe data is in thousands and we would like to have it in, let's say, billions. Yeah, rather so that the interpretation will be easier of the outcomes. Yeah. Right, so let's start with an example for, let's say, data scaling. Here is a model for predicting birth weight of an infant. Birth weight is a function of smoking habit of a pregnant mother and the family income. 6 here is measured as the number of cigarettes smoked by the mother while pregnant each day, and family income is the family income, annual family income in thousands of dollars. And birth weight is in ounces. It's the weight of the child at birth. Let's now have a look at the estimated equation. So we have 3 equations here. Ignore the second and third equation for now. Let's look at the baseline model with the original data. So as you can see, the effect of cigarette smoking on birth weight is statistically significant. So this coefficient estimate has a t-statistics of minus 5.06. That's a huge value. Yeah, so it's a very statistically significant effect, and a coefficient estimate of minus 0.46. So to give you sort of an idea about the effect here, or practical importance, if a woman smokes 5 cigarettes per day, the birth rate predicted to be 2.3 ounces less for a child. Yeah, so this is practically a significant effect. In fact, if imagine this person smokes 1 pack a day or 1.5 packs a day, this results in a huge reduction in the weight of a child at birth. So let's say now that we would like to convert the birth weight from ounces to pounds, yeah, rather, yeah. So in that case, what do we need to do? Well, we will take the data, birth weight data in ounces, and divide each observation through by 16, by a factor of 16, so that the result is pounds. So here is the result. So we'll have a new variable defined as birth weight LBs, which is equal to birth weight over 16. Birth weight is the original data, divide them through by 16. Yeah, so it's now in pounds. So what does it entail? It basically entails this. By dividing the dependent variable by 16, we essentially dividing each coefficient estimate by 16 as well. Yeah, so beta 0 hat divided by 16, beta 1 hat by 16, and also beta 2 hat by 16. Or in the same way, or any other added variables coefficient will be divided by 16 if we convert the birth weight by divide the birth weight by 16. We don't usually divide coefficients by 16 manually. This is all done by the econometric package. Yeah. So what happens now to our equation? So what's the sort of effect of that transformation? So here it is. Yeah. So this is the original result that was as before, so nothing changes here. But notice what happens here. It's the coefficient estimates. Each of these are now different. Yeah. However, what's not different is the r squared. You can see that we didn't add any information that would change the fit of the model, or that would change the data at all. Yeah, we simply rescaled the birth weight data, and adjust. What happened is it adjusted the econometric package adjusted the coefficient estimates only here. Nothing has changed. So observations are the same as before. We didn't drop anything. And those numbers, by the way, so let's start with the coefficient estimate here. So this result here is now reflecting the pounds, yeah, rather than the ounces, the effect in pounds. So it's basically minus 0.02 or minus 0.03 is basically 60 times less than this one here, as it was in the original case. Yeah. So if you multiply the new coefficient estimate by 16, you simply get the original original result. Yeah, that's the same thing. Similarly, the standard error will also decline by a factor of 16. So if you multiply the new standard error for this coefficient estimate by 16, you get this original case. Yeah, so interpretation works in the same way, but this time you simply say that the one pack now, yeah, sorry, not one pack, one cigarette a day or 5 cigarettes per day will reduce the birth weight by 0.03 pounds. That's the interpretation. As you can see, the fit of the regression model doesn't change. It's adjustment to the coefficient estimates that will be. Okay, so what if you'd like to change one of the, let's say, independent variables? Yeah, in this case, let's say 6. What if we want to change it to packs rather than in keeping it in original 6? Yeah, in other words, maybe some people smoke a lot. Yeah, so it's sometimes better to interpret the results in terms of packs of smoked cigarettes rather than cigarette numbers, yeah, or the individual cigarettes. So in that case, what we do is that we will simply divide the cigarettes variable 6 in our, usually this is done in statistical package. We divide the variable 6 by 20, which simply means one pack. Yeah, because each pack contains, oops, my handwriting is so bad here. So each cigarette is each pack contains 20 cigarettes, in other words. Yeah, what does this entail in that case? Well, nothing on the left hand side and nothing to the coefficient estimate of the variables that are not being converted or transformed into a different variable. It's this variable only, sig variable, whose values will be different. In this case, now dividing each observation by 20, we are basically converting it to a pack. Yeah, so here is a new variable. After that, we have a new variable named pack based on this formula. But with this transformation, we're also transforming the coefficient estimates essentially. Yeah? So we multiply the beta 1 hat by the same number that we are dividing the 6 with. So if we divide cigarette by 10, then we have to multiply beta 1 by 10. Since this is 20, we multiply this by 20 as well. Okay, how does it look when estimated as a new equation? So here's the new equation with a new coefficient estimate. Notice this now. This is minus 9.268, which is basically 20 times more than this. So both the standard error and coefficient estimate are multiplied by 20 in this case. But notice that nothing changes here. So nothing is different here. Yeah, nothing is different here in this case. Yeah, that's because we only transform one variable. And notice again that we are not adding any additional information. We simply rescaled the whole all observations by constant 20. Yeah, so no new information is added. So it just simply transforms the the transformation is simply is reflected in the coefficient estimates only. Next issue that we'll be looking at is the standardization or beta coefficients. Now sometimes we would like to, let's say, compare let's say if we have this equation, let's say this is an equation with a number of variables here, we may want to say such as the x1 has greatest effect on y compared to x2 and xk, let's say. Yeah, so you would like to compare the betas, in other words, or the effects of each of these variables. But when you have each of these variables containing different units of measurements, let's say this is in pounds, this is in dollars, this is not dollars, let's say this is in kilograms, this is in miles, so a lot of different factors. Yeah, it's measured in different units of measurement. When we say this increased by $1,000 or this increased by, let's say x2 increased by 2 kilometers, we won't be able to compare their effects. Essentially, yeah, we won't be able to say which one has, in terms of magnitude, has the highest effect. So what we do now is we convert these variables into unit free form, such that we don't have to pay attention to the units of measurement, and this allows then us to compare the magnitudes of the beta. Right, so what we do is we will now standardize the variables, and as you know, standardization is basically done well, this is your z-score usually. You learn this in basic statistics. A z-score is basically it's unit-free form of the data, standardized form of the data. Yeah. So xi minus x bar, standard deviation of x. So that would be the transformation of our of our variable. To do that, we will take away the means of each variable from from their observations, I should say. So for each variable, we just express them in their deviation from the mean forms, and then we divide them through by their standard deviation. And there's one important part here, is that when you divide this y, or the standardized y variable, by dividing it by its standard deviation, you have to do the same thing to the right hand side of the equation, so that when you want to go back to the original form, you will be able to cancel them out, yeah, in that fashion. Yeah, so that's one transformation that's necessary here. And for x's, it's the same thing. You express the x's in deviation form, divide them by their respective standard deviations, but at the same time now multiply the betas by the standard deviations, yeah, so that it also allows us to cancel this out when we want to come back to the original regression model. So this essentially, this expression here taken together, let me just delete this. So this expression, the multiplicative expression and division, or the ratio of standard deviations times the betas, will be our new beta when we standardize the variables. So here now, this is our z1 basically, yeah, z1, or the standardized form of x1. This is our zk. It goes on like this. So our new equation will then be this equation. So if we estimate this, then we get b1 hats, b2 hat, and so on and so forth. So interpretation is the same as before, except that in this case, the b1 hat is basically the effect of z1 on zy, or the standardized x1 on standardized y. Now we usually say this: when x1, or the whatever the variable here, when x1 increases by one standard deviation, the y variable, or the dependent variable, increases by or decreases by b1 hat, yeah, by this amount basically. So we are basically interpreting them in terms of standard deviation changes, yeah, rather than, let's say, millions or thousands or kilograms or miles, yeah. That now this transformation now allows us to say something about or compare the magnitudes of each of these beta coefficients. Now the next issue is if our data is in nonlinear form. Let's say we are dealing with this form of data, scattered in this form. Well, this is y, this is x. We won't be able to capture the data properties well with a linear model like this. We would need a non-linear model here, something like this, yeah. So it goes like this, yeah. So y1 hat would be the better fit than the y0 hat here, right? So the equations that fit this kind of data are called polynomial equations usually. So we'll look at the quadratic form today as an issue, or one of the issues that need to be addressed in our lecture. So let's assume that there is a wage equation which is modeled as a quadratic function of experience. In other words, this form, yeah. In this form, as you can see, at lower levels of experience, additional year of experience adds, let's say, high amounts of wage increase, yeah. There is a high amount of wage increase, but as the experience as we gain experience, the effect of additional experience is decreasing, yeah. So there is a diminishing effect, or diminishing marginal effect of experience kicks in somewhere here, let's say, yeah. So to capture that profile, we usually use the quadratic equation model here. Now for this form, we would need to get a negative coefficient of experience squared, or x squared, yeah, in any with any variable. So this has to be a negative beta here. This has to be negative beta to get this kind of form. Now how do we interpret this now? It will not be possible to say, let's say, 1 unit increase in experience, holding experience squared constant, will be this much. No, we cannot say that. That's because if you increase this experience variable by 1 unit, then obviously you have to increase this by 1 unit as well. Both of them are the same variable. We have this formula for interpreting the result. Now, where do we get that formula? Let me just clean this up. We use calculus, derivatives, to calculate the marginal effect. So what we do, we take the derivative of wage with respect to derivative of experience. What do we get here is then that will be 0, that would be 0.298, and minus 2 times, so now derivative of this, that times 61 experience. So this will be our new formula for interpreting the marginal effect of experience on wages. In other words, the effect of experience on wages depends on the initial amount of experience, or initial experience. In this case, what if it is a different variable than initial value of x here, right? So let's do this exercise quickly. So let me just clean this. Let's say change in wages when experience changes is equal to 0.298 minus 2 times the value here of the coefficient estimate times, let's say experience increased from 0 to 1 year. Yeah, so initial year was 0. Then you will get a coefficient estimate here of 0. Let's say roughly 30. Yeah? So additional year experience from 0 to 1 basically increases our wage by that much. Yeah, but let's say we take this change in wages with respect to experience, 0.298 minus 2 times 0.0061 times, now we're looking at now the effect of the second year in addition into our experience. Yeah, so our experience increased from 1 to 2. In other words, we added one more additional year of experience starting with the first year as the initial year. So that's going to be times 1, and that gives us something like 0.29. Let's say in this case dollars. Yeah, so what you will see here is that as our experience level increases, the marginal effects start declining. Yeah, in the initial case it was that much, now it's this much, and as we add more, or as we progress in our experience, additional years of experience will add diminishing marginal returns, yeah, to our wages. Okay, so that's how we interpret this result here. Graphically, this is how it looks basically with this example. So because there is a turning point, we can always find a maximum point, and unfortunately with the quadratic equations we have these two parts of the curve. Let me just draw this. So if data looked like this and our model fitted equation or the function in this form, kind of a inverse u, then we should be very careful in interpreting this part here. This part is basically redundant. Notice this additional year of experience is basically experience here is wage here, additional year of experience adding a negative wage here. Yeah, so the marginal effect is negative from this point onwards. Yeah, so we need to be careful with this sort of interpretations or the functions. So we would need to find the turning point or experience corresponding to the turning point, and we would be then looking at the values of experience up to that point. Yeah, beyond this point the values of experience will not add much apparently. It basically is going to give us a negative marginal return, so we will be ignoring that part. So how do we get that? We take the derivative, so delta w delta experience, if you remember, was beta 1 minus 2 beta 2 x. Yeah, so now set this to 0 and solve for x. That gives us x equals then beta 1 over 2 beta 2. Now we take the models of this result, because x here, in this case experience, doesn't take negative values, so that the outcome, whatever outcome here, will be a positive value, yeah, positive outcome. So in this example, we plugged in the coefficient estimates. By the way, these are hats here, yeah? I forgot to put these hats. So if you plug in the estimated coefficients, you get 24.4 years. So we shouldn't be predicting the wages for years of experience greater than 24.4, because it turns out the marginal effect of additional year of experience after that year will usually give us a negative wage, which doesn't make sense. We would expect that as we gain experience, our wages would increase, yeah, rather than decreasing. Yeah, we wouldn't see that in practice unless there's something terribly happens and we get a job or demotion, let's say. Yeah, but in this case, the additional years of experience should be adding a positive wage, yeah, or should contribute towards the wage positively. So we will ignore this part. Now you might want to say why this happens. Well, it's possible because most of our data is on the left hand side of, yeah, to this point, yeah, left to this point, yeah, most of our data, and some data points will lie here. So the OLS, they will try to capture that point, yeah, these points, a few points here, and then it ends up imposing this sort of downward sloping part of the curve. But we will ignore that, because on to this side, to the right of the equation, usually we only have fewer points, we can ignore them. Another important point here is that maybe we have omitted variable bias. Maybe some variables that are important here are not added. So if I go back here, as you can see, this is a very simple function of wage, and we would expect the wages to be function of many other variables. So productivity measures, intelligence, the management style, and many others would usually add to our wages. So that's why we may feel or we may get this sort of results. Next, what if we have a situation like this, where we actually have sort of an increasing marginal returns, yeah, increasing marginal returns in our data, for example. So let's say the log price here, price of house and rooms. So if we are valuing a house and assessing its value, we know that additional rooms add value to the price of the house. So when, let's say this is a 4-bedroom house, this is 5-bedroom. So if we add the next bedroom, we see some increase in our house price. Let's add more bedrooms, some increase, but then eventually, as house gets bigger and bigger, we would expect that the house price will be sort of accelerating as well, yeah, so increasing in value. So additional rooms eventually will add much more than when the house was smaller, yeah. So this sort of relationship can be captured by a quadratic equation as well. However, this time the signs of the coefficient estimates will be different. So let me put this down, what we expect in this sort of relationship. In this case, so that's beta 0 plus beta 1. Oh no, so this is negative x1, oops, I got the wrong color, beta 2 x1 squared. So if this were the room variables, then we have room here and room squared, but notice now this is a positive beta 2, yeah, positive beta 2, while beta 1 is negative. In this fashion, we will be able to get this kind of fitted line in our data. So maybe our data scatters around like this, yeah, like this. A lot of them to the right side of the sort of this U shape, but maybe some more here, some more, a few there, not much, but a lot of them right here. And yeah, here it is. So interpretation will be the same as before. It depends on the initial number of rooms, and as you can see, the equation is much the same as before. So this is, in this case, is simply a percentage change, yeah, because of the log price being the dependent variable. Yeah, so this is graphical explanation. So we will just cut the part. So it looks like this here, but we just cut this part, and then we're trying to find the minimum point after which the changes in x induce increasing returns in y, yeah, while before that point the change in x usually have a negative sort of return or negative effect on y. Now, why is that happening here? It's because maybe to the left of the minimum point here, in this case 4.4 rooms apparently, there are only few points, few data points, and Euler tries to capture them as well, but after this point most of the data lies, most of the data lies after this point. So we usually ignore, just like in the other case, we ignore this part of the fitted line, and we start as a minimum point for prediction purposes from 4 or 4.5 rooms, let's say, and onwards. So if you would like to predict an additional effect of an additional room on the house price, then we start, let's say, from by adding 5 to 6th room. So we keep 5 as the initial point and then increase the room size into 1. So that way we'll be able to predict the price change of adding an additional room. So let's look at this example here. Here is the beta 1, here is the beta 2, and initial value is 5. When we increase the rooms from 5 to 6 in our house, what happens to the price? Well, price increased by 7.5% apparently points. Now, what if we increase the space of the house by adding one more room? Let's say we increase it from 6 rooms to 7 rooms in our house. Well, in that case, the beta 1 stays the same. We just simply replace 5 here with 6, and that gives us an even higher price increase. So it's basically the case of accelerating impact, increasing marginal returns to x, changes in x. So as we add more rooms, the effect on price will be higher. That makes sense. The larger the house, higher the price. So given this negative beta 1, we should be careful, because when you add, let's say, you increase the rooms from 3 to 4, then you will get a negative percentage increase in price. So in this case is because there are fewer houses with small number of rooms. So let's say 2-bedroom and 3-bedroom and 4 bedrooms, there are few of them. So as a result, this part of the fit is not good. So we will be focusing on this part of the fit, and then we'll be adding for prediction purposes, we'll be dealing with the numbers of rooms greater than 4.4. Okay, so that's all about the quadratic equation and then the associated issues.